want to move to the new subtopic, which is the polarity of the molecule. Okay, we have learned, okay, the polarity of the bond before. Okay, and now we want to continue with the polarity of the molecules. Okay, so this polarity of the molecules is actually arise from a polar bond. Okay, so let's refresh back. What is a polar bond? Okay, it is actually a bond that is made between the two atoms that have different in their electronegativity. Okay, so different in electronegativity means that they have different in the ability to attract the electron. Okay, so due to that, okay, it will mix the bonded electron. Okay, they are sharing the electrons, right? Okay, in a bond. So when they have different ability to attract the electron, it will make the electron density become imbalanced. The electron will be higher, okay, the electron density will be higher at the one that is more electronegative. Okay. And then we always choose the polarity of the bond by using this vector quantity, this symbol. Okay, this cross and arrow. Okay, in which okay, the cross n is at the one that is more electropositive and the arrowhead at the one that is more electronegative. Okay, so that is, we talk about polar bond. Now we want to talk about the polar molecules. Okay, polar molecules is when we have a dipole in a molecule. Dipole means two pole. Okay, the positive pole and the negative pole that can be distinguished. Okay, we can identify, okay, where is the positive pole and where is the negative pole of the molecules. If we can distinguish that, if we can identify that two different pole, okay, only two poles, it cannot be more than that. Okay, then we said that the molecule is a polar molecules. Okay, example is given here when we have a carbon dioxide. Okay, so the carbon dioxide, we know that the bonds in a carbon dioxide are all polar. Okay, this bond is polar, same goes with this bond. Because oxygen is more electronegative than carbon. So due to that, this bond polarity is moving towards oxygen. Same goes with this. Okay, the bonds are all polar, but now the molecule as a whole is not necessarily polar. Okay, it is become polar or non-polar depends on the shape of the molecule. That is why we have to know, okay, to identify how to identify the correct molecular geometry or the correct molecular shape before we can identify the polarity of a molecule as a whole. Okay. So if we look at to this HF, okay, we know that in an atom, okay, they are having electron cloud. Okay, obviously since that the fluorine is more electronegative than the hydrogen, the bond become polar. Okay, the bond become polar towards fluorine. Okay, and then when we look at the molecule as a whole, we also observe that there is an imbalance here. Okay, it is not symmetry, tak sama. Okay, we observe that this side is more bigger than this side. Okay, this is the electron cloud. Okay, so due to the difference in the electron density, makes the molecules or the electron cloud become imbalanced, asymmetrical. Okay, makes this molecule become a polar molecule because it is obviously that this side have a higher electron. Okay, or the electron density at this side is higher as compared to this side. That is why the electron cloud is bigger. So when we can distinguish that this is the negative pole, okay, and this is the positive pole of the molecule, so we say that this is a polar molecule. Okay, it is obvious for the one that have only two atoms. Okay, example in HF. Okay, so what is the dipole moment? Okay, the value of the dipole moment is used to determine the polarity of the molecule. Okay, so the greater the dipole moment value, the more polar the molecule. So if we have a polar molecule, okay, the dipole moment or the mu will be not equal to 0. Okay, means that it is greater than 0. As long as we have a value for the dipole moment, then we know that the molecule is a polar molecule. However, if the dipole moment or the mu is equal to 0, okay, if the dipole moment is equal to 0, means that the molecule is non-polar molecule. Okay. So let's look at to the example HCl as what we have seen just now. Okay, the bond in the HCl is polar. Okay, this bond is polar towards chlorine. Okay, and then the molecule as a whole also polar. Okay, that can be represented by this resultant dipole moment. It is the same as this arrow. Okay, but it is bigger to show the final dipole moment of a molecule. Okay, the resultant dipole moment, okay, is moving towards chlorine. Okay, the arrowhead at the chlorine side. So this is the negative pole and this is the positive pole of the molecule. So that the total dipole moment is not equal to 0. Okay, the mu is not equal to 0. So the molecule of the HCl is a polar molecule. Okay, as compared to the carbon dioxide, we know that there is no lone pair at the central atom. Okay, there is no lone pair at the central atom. Okay, it makes the shape of the CO2 become linear. Okay, so this bond is polar and moving towards oxygen. And this bond also polar moving to the left. Okay, so the dipole moment at this side is to the right and this side to the left. Okay, however, since that the shape is linear, okay, so the mu or the dipole moment can cancel out each other. Okay, it will make the resultant dipole moment or the final dipole moment become equal to 0. So that the carbon dioxide is a non-polar molecule. Okay, that is why we have to know the correct shape. However, if let's say we have a CO, if let's say you wrongly determine the shape of the CO2, okay, you make it bent. Okay, if you make it bent, then now, okay, the resultant dipole moment, okay, since that they both of them towards oxygen, okay, we will have a resultant dipole moment, okay, that is downward. Okay, because it is like vector that we have learned in our school time. Okay, when the force is actually right, okay, actually the resultant, they are sum, right? Okay, their force is actually, the total is actually downward. Okay, it is the same kalau macam ada orang, okay, tarik 3 tali. Okay, sebenarnya total dia tu downward kan? Okay, it is the same as this is a vector, the basic vector. Okay, that is why if the shape is wrong, then it might leads to wrong polarity of a molecules. So since that the shape is linear for the carbon dioxide, okay, the dipole moment cancel out each other. It makes the carbon dioxide become a non-polar molecule. Okay, so if we have a covalent bond that is made between the same atom, okay, the bond is made between the same atom. Example is fluorine bonded with fluorine, oxygen bonded with oxygen, nitrogen bonded with the nitrogen. Okay, it will mix all bonds become non-polar. Okay, the bond in the molecule non-polar. Okay, it means that the bonding electrons, okay, the electrons that they shared are shared equally. Okay, the electron distribution are balanced. Okay, and it will make the molecule become non-polar. Okay, if the bonds are all non-polar, the molecule will always non-polar. Okay, if we have the non-polar bonds, the molecule will never be polar. Okay, however, if the covalent bond is made between different atoms that have different in their electronegativity, okay, we know that the bonding electrons are closer. Okay, the electron that they shared will be closer to the one that is more electronegative. Okay, so if the bonds are polar, okay, the molecule could be polar or non-polar. Okay, and it is actually depending on the shape. Okay, if the bonds are non-polar, okay, let me conclude and recap. Okay, if the bonds in the molecule are all non-polar, the molecule will never be polar. But if the bonds in the molecules are polar, okay, there will be two possibilities. Okay, it's either it is a polar or they are non-polar, and it is also depends on the shape of a molecules. Okay, so let's look at to the other example when we have a CCl4. Okay, we know that CCl4, it has 4 terminal atom. 1, 2, 3, 4 terminal atom. Then the shape will be tetrahedral. Okay, we have to remember the shape. Okay, we have to correctly determine the shape of a molecule first. Okay, the shape is tetrahedral, and then we look at to the bonded atom, chlorine, 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 and all chlorine are more electronegative than the carbon. It makes the bonds are all polar in this molecule towards chlorine. Okay, so this is the polarity of this bond, the polarity of this bond, the polarity of the bond, and the polarity of this bond. Okay, so we have one dipole moment upward, okay, in which it is actually cancelled out with the combination of these three force downward. Okay, these three combine, okay, the force downward is actually the same as one force upward. Okay, makes the dipole moment cancel out each other, and this molecule of the CCl4 as a whole is a non-polar molecule. Okay, in which even though all bonds are polar, but since that the shape is a tetrahedral, so all atoms are symmetrically arranged. Okay, it will make the molecule as a whole become non-polar molecule. Okay, another example is the SF6. Okay, so we know that SF6 is octahedral. Okay, if I redraw back the structure, we have a sulfur. Okay, it has octahedral with 6 terminal fluorine. Okay, the bonds are all polar towards fluorine. Okay, so the dipole moment of that fluorine, okay, cancel out with the dipole moment here. Okay, they cancel out this with this. Okay, and then the dipole moment upward cancel out with the dipole moment downward. And then the dipole moment to this fluorine cancel out with the dipole moment to this fluorine because they are oppositely to each other. Okay, it will mix the resultant dipole moment become equal to 0. Okay, when the mu is equal to 0, the molecule is a non-polar molecule due to the shape that is octahedral. Okay, the shape is octahedral, it will be non-polar if we confirm that all terminals are the same, fluorine. Okay, it is also possible if we have different terminal atom. We have a mixture of atoms. Okay, at that time, okay, the molecule might be polar. Okay. Example, I'll give you example if let's say it is not fluorine. Okay, it is not fluorine. We have a chlorine, for example. We have a mixture of chlorine and fluorine. So chlorine, chlorine, chlorine. Yes, we know that all bonds are polar. Okay, however, the dipole moment will be different. Okay, this dipole moment is not the same. The force here towards chlorine is not the same as the force towards fluorine. Okay, because fluorine is more electronegative than chlorine. Okay, it means that it is not totally cancelled out. We still have a dipole moment value that is not equal to 0. Okay, but if they are all the same atom, okay, then the molecule become a non-polar. Okay, let's look at to this example. We have a CHCl3. Okay, CHCl3 that is arranged in a tetrahedral shape. Okay, we have a terminal hydrogen, chlorine, chlorine, and chlorine. Okay, the bonds are all polar. Okay, hydrogen, carbon. Be careful when you determine the polarity of the bond. Okay, hydrogen and carbon. Okay, carbon is more electronegative, so the bond polarity here will be towards carbon. Carbon, chlorine, yes, chlorine is more electronegative, so polarity towards chlorine, chlorine, chlorine. So the combination of these three will be downward. Okay, and then it is actually added with this dipole moment, which is also downward. Okay, this one combined with this, so that we will have a resultant dipole moment for the whole molecule, which is downward. So the molecule is a polar molecule. When the resultant dipole moment is downward, then it means that we know that the lower part will be the negative pole, the upper part is the positive pole of the molecule. It has two pole, dipole, then it is a polar molecule. Okay. So this is the example that I said just now, even though it is tetrahedral, when the terminal atom are different, okay, it might lead to a polar molecule. Okay, but if let's say they are all chlorine here, if let's say here is also chlorine, so that this bond polarity will be moving towards chlorine. Okay, since that the shape is tetrahedral, they will cancel out. Okay, the force upward cancel out with the combination of these three that is downward. It will make the molecule become non-polar. But for this, okay, since that this atom is hydrogen, okay, so it is a polar molecule. Okay, another example, CH3Cl. Just now chlorine is 3, hydrogen 1. But this time hydrogen 3, chlorine 1. Still we have a tetrahedral shape. Okay, hydrogen and carbon. Carbon is more electronegative. So these three are moving to the carbon. So the combination of these three is actually upward. Okay, and then carbon to the chlorine. Chlorine is more electronegative. So the bond polarity towards chlorine upward. So it means that this dipole moment combine with this dipole moment so that it relates to the resultant dipole moment of a whole molecule, which is upward. Okay, so when we have a resultant dipole moment, it means that the mu is not equal to 0 and the molecule is a polar molecule. Okay, if we have a SO2, okay, SO2, the shape is bent. H2O also bent. Okay, and then we look at to the sulfur and oxygen. Oxygen is more electronegative. So when oxygen is more electronegative, okay, these two, okay, that is actually combined and it makes the resultant dipole moment downward. Okay, the resultant dipole moment of the whole molecule is downward. The molecule is a polar molecule because the mu is not equal to 0. Same goes with the H2O here. Oxygen, hydrogen, we know that oxygen is more electronegative. So the combination of these two dipole moment, okay, is actually upward. So that our resultant dipole moment will be upward. Okay, and the H2O molecule is a non-polar molecule. But if you wrongly give the shape of the H2O, okay, before you learn the shape, okay, normally student will draw the structure of H2O like this. There are two lone pairs, one above and one below the oxygen, as if the shape of the H2O is linear. Okay, if you write it as linear, okay, if let's say the shape is linear, okay, we know that this bond polarity towards oxygen, this bond polarity also towards oxygen, and if it is linear, they will cancel out each other, then the molecule become non-polar. Okay, however, this is the wrong shape. Okay, it is actually bent. Okay, and due to the bent shape makes the H2O molecule is a polar molecule. If we have a ammonia, okay, ammonia have a trigonal pyramidal shape. Remember? Okay, trigonal pyramidal shape. Okay, in which nitrogen and hydrogen, nitrogen is more electronegative, makes the bonds are all polar, and the polarity, the dipole moments are moving towards nitrogen. Okay, and when these three combine, it will make the resultant dipole moment of this molecule is upward. Okay, so when the mu is not equal to 0, the molecule is a polar molecule. Okay, and F3. Okay, NF3, the same shape as the NH3. Okay, H3, and this is the NF3. Nitrogen, fluorine. Fluorine is more electronegative. Okay, fluorine is more electronegative, so the bond polarity here moving towards fluorine. So the combination of these three, okay, will makes the resultant dipole moment become downward. Okay, this is the resultant dipole moment. So both of these two molecules are polar, and H3 polar and F3 also polar. Okay, however, we look at to the value, the mu value. Okay, the resultant dipole moment value. Okay, we observe that ammonia has a resultant dipole moment value 1.46. As for the and F3, the mu is 0.24. Okay, so we observe that this is greater than this, means that ammonia is more polar than an F3. Okay, both are polar, but ammonia is more polar because of the greater dipole moment value. Okay, so we have seen all this. Okay, H2O is a polar molecule. Why it is polar? Because the dipole moment is not equal to 0. Okay, and the shape is bent, so the resultant dipole moment in this case is upward. Okay, CO2, okay, the dipole moment is equal to 0. Okay, no dipole moment, it is equal to 0 because of the shape that is linear, so it is a non-polar molecule. As O2 is a polar molecule, the resultant dipole moment is downward. Okay, CH4, okay, this is the wrong shape, it's supposed to be tetrahedral. Okay, we have to draw it correctly. Okay, and dipole moment is equal to 0, so it is a non-polar molecule.